Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
A quiet revolution in human reasoning began with the formula of elegant, almost deceptive, simplicity. It provides a formal mechanism for something we do intuitively every day, updating our beliefs in light of new evidence. This intellectual engine, a cornerstone of modern statistics and artificial intelligence, is known as Bayes' theorem. It gives us a precise way to quantify how confident we should be in a hypothesis after observing a piece of data. The theorem is expressed as follows: the probability of a hypothesis H, given some evidence E, is equal to the probability of observing that evidence E if the hypothesis H were true, multiplied by the initial probability of the hypothesis H being true, all of this divided by the overall probability of observing the evidence E. To grasp its power, consider a common scenario in medical diagnostics. Imagine a test for a particular disease. The hypothesis, H, is that a patient has the disease. The evidence, E, is a positive test result. The theorem requires us to consider several pieces of information. First is the prior probability of the hypothesis, written as P of H. This is our initial belief, the prevalence of the disease in the general population before any test is run. Perhaps it is 1%. Second is the likelihood, the probability of the evidence given the hypothesis, written as P of E given H. This represents the test's accuracy if a person has the disease. What is the probability the test will correctly come back positive? Let us say this is 99%. We also need to account for the test's fallibility. The overall probability of a positive test, P of E, includes both true positives and false positives cases where healthy individuals receive a positive result. If the false positive rate is, for instance, 5%, the calculation reveals a profoundly counterintuitive result. Even with the positive test, the updated belief, the posterior probability that the patient actually has the disease, is far below what one might expect. The initial rarity of the condition exerts a powerful gravitational pull on the conclusion. This single, elegant piece of mathematics forces a disciplined accounting of uncertainty, tempering our conclusions with a rigorous dose of prior context. The creation of this theorem was a response to a deep, impressing intellectual challenge of the 18th century. The era was one of profound confidence in reason and the power of mathematics to decode the universe. The scholars had made immense strides in what we might call forward probability, calculating the likelihood of future events given a known set of causes. If one knows a die is fair, one can calculate the probability of rolling a 6. If one knows the exact composition of an urn of colored balls, one can determine the chances of drawing a red one. The great minds of the age were preoccupied with this calculus of chance. Thomas Bayes, a Presbyterian minister and amateur mathematician living in Tunbridge Wells, England, turned this entire problem on its head. He was concerned with the inverse. His question was far more subtle and, ultimately, far more useful for empirical science. Suppose we observe an effect, a series of successful outcomes in some unknown process. What can we infer about the underlying cause, the intrinsic probability of that success? We see the world's data. We wish to know the parameters of the machine that generates it. This is the problem of inverse probability reasoning from observed consequences back to their unobserved causes. It is the fundamental problem of all scientific inference, of learning from experience. Bayes was working within a rich intellectual tradition. The groundwork for his inquiry was laid by brilliant predecessors whose work he would have studied with care. The Swiss mathematician Jacob Bernoulli, in his posthumously published masterpiece, *Ars Cogitandi* from 1-7-10-13, had established the law of large numbers. Bernoulli demonstrated that as the number of trials increases, the observed frequency of an event will converge upon its true underlying probability. This was a monumental achievement, linking empirical observation to theoretical probability. It answered a forward-looking question with enough data. We can become almost certain of the outcome's frequency. Yet it left the inverse question unanswered. Knowing that observation converges on truth is one thing, quantifying our certainty about that truth after a finite, and perhaps small, number of observations is another matter entirely. Another towering figure whose influence is palpable is Abraham de Moivre, a French Huguenot refugee who became a leading light of London's scientific community and a close associate of Isaac Newton. De Moivre's more 1780 work, The Doctrine of Chances, was a preeminent textbook on probability theory of its day. He extended Bernoulli's work, developing an early version of the central limit theorem by showing how the normal distribution, the familiar bell curve, could approximate the binomial distribution for a large number of trials. De Moivre was a master of calculating the odds of complex events, pushing the mathematics of forward probability to its limits. Bayes, working in this environment, took the logical next step. He sought a formal method to invert the direction of inference, to build a bridge from de Moivre's world of known probabilities to the empirical scientist's world of unknown causes. His solution was presented to the world under circumstances that have added to his mystique. Bayes himself published almost nothing during his lifetime. It was his friend, the polymath and philosopher Richard Price, who discovered the crucial manuscript among Bayes' papers after his death. Recognizing its profound importance, Price edited the work and presented it to the Royal Society in 1763. Its title is Revealing an Essay Towards Solving a Problem in the Doctrine of Chances. The wording is modest, a single contribution to an ongoing conversation. The essay uses a clever thought experiment involving a ball thrown on a square table to derive a general principle for inferring an unknown probability. It established, for the first time, a mathematical justification for learning from data, providing a formula to update one's degree of belief as new evidence accumulates. This single essay planted a seed that would take nearly 2 centuries to fully germinate. Today, the principle it contains is the foundation of an entire branch of statistics known as Bayesian inference. Its logic underpins vast swaths of modern technology, from the spam filters in our email to the complex models used in machine learning and artificial intelligence that allow systems to learn and adapt. It provides a mathematical language for uncertainty, a framework that allows a machine or a scientist to weigh evidence, update beliefs, and make predictions in a world of incomplete information. Having established the theorem's conceptual power and historical origins, our inquiry must now turn to into its internal architecture. We will proceed to dissect the rigorous mathematical derivation of the formula itself, examining the precise definitions of its components and the assumptions that give it coherence. From there, we will trace its intellectual lineage forward, exploring how subsequent mathematicians like Pierre-Simon Laplace formalized and vastly expanded upon Bayes' initial insight, and how the theorem's elegant logic continues to shape the very frontiers of computational science and statistical reasoning. The theorem's architecture, a marvel of logical economy, arises directly from the foundational axioms of probability. Its elegant power is a consequence of a simple, yet profound, rearrangement of the definition of conditional probability itself. To appreciate the structure Bayes erected, one must first revisit the ground upon which he built. The concept of conditional probability, the likelihood of an event occurring given that another has already transpired, was a familiar idea to the mathematicians of his era. The work of Abraham de Moivre, particularly in his seminal text The Doctrine of Chances had provided a formal language for such dependencies, primarily in the context of gains and actuarial problems. De Moivre had established the multiplicative rule for probabilities, articulating that the probability of two events, A and B, happening together is the probability of A occurring, multiplied by the probability of B occurring given that it has already happened. This is expressed as the probability of A and B equals the probability of A times the probability of B given A. Bayes began his reasoning from this very point. The insight that unlocks his entire framework is the recognition that this relationship is symmetric. The probability of A and B occurring is identical to the probability of B and A occurring. Therefore, one can express the joint probability in two equivalent ways. First, as we have seen, the probability of A and B is the probability of A times the probability of B given A. Second, it is also the probability of B times the probability of A given B. Since these two expressions equal the same quantity, they must equal each other. This yields the equation the probability of B given A multiplied by the probability of A equals the probability of A given B multiplied by the probability of B. With a simple algebraic division, the celebrated theorem emerges: the probability of A given B is equal to the probability of B given A multiplied by the probability of A all divided by the probability of B. This formula, while mathematically straightforward, represents a radical reorientation of inference. Each term within it carries a specific and powerful meaning. The quantity we seek to calculate, the probability of A given B, is the posterior probability **. It represents our updated degree of belief in a hypothesis A after we have observed some relevant evidence B. The term on the far right of the numerator, the probability of A, is the *** prior probability **. This is our degree of belief in the hypothesis before the introduction of new evidence. It encapsulates all pre-existing knowledge, assumptions, or information about the hypothesis. Connecting the prior to the posterior is the ***, likelihood ***, represented by the probability of B given A. This term quantifies how probable it is that we would observe the evidence B if our hypothesis were actually true. It is the engine of the inferential process, the mathematical link between data and theory. A hypothesis that makes the observed evidence highly probable will see its own probability boosted. Finally, the denominator, the probability of B, is the evidence or marginal likelihood **. It represents the total probability of observing the evidence B across all possible hypotheses. This term serves as a normalization constant, ensuring that the sum of all possible posterior probabilities equals 1, thereby maintaining logical consistency within the probabilistic framework. The genius of Bayes' formulation was its application to what we now call the problem of inverse probability. The probabilistic work of his predecessors, like Bernoulli and de Moivre, was overwhelmingly concerned with direct probability given a known underlying cause or parameter. What is the probability of a certain outcome? For instance, given a perfectly fair six-sided die, what is the probability of rolling a 4 3 times in a row? The problem Bayes set for himself in his essay was the reverse. Given a set of observed outcomes, what can we infer about the unknown underlying cause? Given that we have rolled a 4 3 times in a row, what is the probability that the die is in fact fair? He illustrated this with a thought experiment of remarkable clarity involving a square table, what we might call a billiard table. Imagine a first ball is thrown onto the table, and its resting place determines a vertical line. The position of this line is unknown. Subsequently, more balls are thrown. For each new ball, we record whether it landed to the right or to the left of the initial unknown line. The problem is to infer the probable location of that first line, the unknown parameter, based on a sequence of subsequent observations. Here, the prior belief might be a uniform one, assuming the first ball could have landed anywhere with equal likelihood. Each subsequent ball, our evidence, allows us to update this belief, narrowing the range of plausible locations for the original line. This was a move from predicting effects from causes to inferring causes from effects. This singular achievement, communicated posthumously through the efforts of his friend Richard Price, found its most powerful champion and extender in the French mathematician Pierre-Simon Laplace. Working initially without knowledge of Bayes' essay, Laplace independently developed a similar principle in his 1774 paper, Mémoire sur la probabilité des causes par les événements, or Memoir on the probability of the causes of events. It was Laplace, in his monumental 1812 work Theorie analytique des probabilités who generalized the principle and demonstrated its vast applicability. He elevated what Bayes had framed as a solution to a specific problem into a universal method of scientific reasoning. Laplace applied it to problems in celestial mechanics, such as estimating the mass of Saturn based on orbital perturbations of Jupiter, and to questions of earthly populations, far beyond the scope of Bayes' original conception. He cemented the theorem as a fundamental tool for learning from data. The mathematical integrity of the theorem is absolute, flowing as it does from the axioms of probability. The challenges and profound debates it would later ignite stem from its application. The selection of the prior probability, the probability of R, introduces a component that can reflect subjective judgment. While Bayes, in his billiard table example, employed a uniform prior, assuming a state of complete ignorance about the initial ball's position, the choice of a prior in more complex scientific problems can be a source of considerable contention. The entire structure of inference depends on this initial assumption. Furthermore, the validity of the conclusion rests on the accurate specification of the likelihood, the probability of B given A. This function is a model of the data generating process. If this model is a poor representation of reality, The Bayesian engine, for all its logical precision, will process floored information and yield a floored result. A final, practical limitation for centuries was the calculation of the evidence term in the denominator. For anything but the simplest of problems, this requires summing or integrating over all possible hypotheses, a task that can become computationally prohibitive. This very obstacle, however, has spurred immense innovation in the modern era, leading to the development of sophisticated computational techniques designed specifically to approximate this calculation and unlock the power of Bayesian inference for the complex problems of our time. The Theorem's mathematical journey from a simple axiom to a complete system for updating belief reveals a structure of immense intellectual beauty and practical consequence. Its pure logic provides a formal mechanism for reasoning in the face of uncertainty. Having now explored this internal architecture, our focus shifts to its initial journey into the world. We must examine how this powerful, yet subtle, idea was first received, applied, and debated by the scientific minds who encountered it in the decades following its quiet publication. The posthumous publication of an idea guarantees its author a certain quietude and immunity from the immediate praise or censure of their peers. For Thomas Bayes, this meant his essay towards solving a problem in the doctrine of chances entered the world in 1763 as a kind of intellectual orphan, presented and interpreted by his friend, Richard Price. Price's role was foundational. He was the theorem's first champion, its initial editor, and the one who framed its grand purpose. In his own appendix to the paper, Price articulated the central ambition to create a method for reasoning backwards, from observed effects to the probabilities of their underlying causes. He saw in Bayes' dense mathematics a tool for epistemology itself, a way to formalize how we learn from experience and update our beliefs about the world. Price himself applied this reasoning to argue for the credibility of miracles, an application that, while reflecting the theological concerns of the era, also demonstrated the immense philosophical scope he envisioned for Bayes' formula. This nascent idea, however, found its most powerful and immediate champion across the English Channel, the French mathematician Pierre-Simon Laplace, a towering figure of celestial mechanics and probability theory, independently arrived at the same core principle. His engagement with inverse probability resulted in a profound rediscovery and a significant generalization of Bayes' work. Laplace's 1-174 Memoire sur la probabilité des causes par les événements presented a more versatile and analytically powerful version of the rule. He proceeded to apply it with breathtaking effect to the most challenging scientific problems of his day. A quintessential example was his work on celestial mechanics, specifically determining the masses of planets. Observational astronomy provided data on the orbits of celestial bodies, which were the asterisk effects asterisk. The underlying asterisk cause asterisk was the gravitational pull, and therefore the mass of planets like Jupiter and Saturn. Using multiple, error-prone observations, Laplace employed his probabilistic method to work backwards, producing an estimate of the mass of Jupiter that remains remarkably close to modern values. He treated observational errors themselves as a probability distribution, inferring the most likely true value from a collection of imperfect measurements. Laplace also formulated what became known as his rule of succession. This is a direct, and perhaps the most famous, early application of Bayesian reasoning. The problem it addresses is simple to state: if an event has occurred n times in a row, what is the probability it will occur on the next trial? Laplace's answer, derived from Bayes' principle with a uniform prior, is n plus 1 divided by n plus 2. The famous, though perhaps apocryphal, example is the probability that the sun will rise tomorrow, given it has risen every day for 5,000 years. The rule provides a quantitative answer, transforming a philosophical puzzle into a tractable calculation. This demonstrated the power of the method to provide concrete, numerical answers to questions of induction. The influence of this new way of thinking extended into the nascent social sciences. The Mark Peter Condorcet, a contemporary and sometimes rival of Laplace, applied similar principles of inverse probability to questions of social choice and legal justice. In his work on jury composition, Condorcet explored the probability that a defendant is truly guilty given a certain verdict from a jury of a particular size and competence. The verdict is the observed effect. The defendant's actual guilt or innocence is the unobserved cause. Condorcet's analysis, while complex and ultimately optimistic about the power of collective reason, represented a pioneering attempt to apply rigorous probabilistic modeling to the mechanisms of human society. It showed that the logic of reasoning from evidence to hypothesis was universal, applicable to the orbits of planets and the deliberations of people alike. Despite these brilliant applications by some of Europe's foremost minds, Bayes' rule experienced a long period of relative hibernation. Its adoption remained confined to a small circle of elite mathematicians. Several formidable obstacles prevented its widespread use. The first and most persistent challenge was philosophical. The entire procedure hinges on the selection of a prior probability distribution, the term pH in our earlier notation. This represents our belief in a hypothesis asterisk before asterisk seeding the evidence. Bayes and later Laplace often relied on the principle of insufficient reason, which posits that if there is no evidence to favor one hypothesis over another, all should be assigned equal prior probability. To many thinkers of the 19th century, this felt like a profound weakness. It seemed to inject a degree of subjective assumption into what should be a purely objective statistical procedure. Critics argued that this was little more than a formal way of quantifying ignorance, and that building a science upon such a foundation was precarious. This philosophical unease fueled the development of an entirely different conception of probability. The frequentist school, which gained enormous momentum through the 19th and early 20th centuries with champions like John Venn, George Boole, and later Carl Pearson and R.A. Fisher, defined probability in a different way. For a frequentist, probability is the long-run frequency of an event in repeated trials. It is an objective property of the world, measurable through experiment. This framework had the advantage of avoiding the troublesome priors of the Bayesian approach. It also offered a suite of powerful, computationally simpler tools for the kinds of problems, agricultural experiments, population genetics, industrial quality control that were becoming central to scientific progress. The statistical methods that emerged from this tradition, such as hypothesis testing and confidence intervals, became the standard language of science for much of the 20th century. A second, deeply practical barrier was computational. The denominator in Bayes' theorem, the marginal likelihood, requires summing or integrating over every possible hypothesis. For Laplace, calculating the mass of a single planet, this was achievable with the formidable analytical tools at his disposal. For more complex problems with many parameters, this integral becomes hopelessly intractable. Without the means to compute this term, the posterior probability remains inaccessible. The elegant logic of the theorem was therefore imprisoned by the mathematical limitations of the era. The very power of the theorem to handle a continuous spectrum of beliefs became its practical downfall. Thus, the initial reception of Bayes' legacy was paradoxical. The theorem was seized upon by the greatest mathematical mind of the age, Laplace, who expanded it and applied it to solve cosmic problems. It was recognized by visionaries like Condorcet as a potential key to a science of society. Yet, for over a century and a half, its progress stalled. It was viewed with suspicion for its reliance on prior beliefs and sidelined by the rise of a powerful and more computationally tractable frequentist alternative. The idea was too elegant to disappear, preserved in advanced texts on probability theory, but it remained largely a theoretical curiosity. It awaited a future era, one equipped with new philosophical arguments and, crucially, a revolutionary new capacity for computation to unlock its full potential and bring it from the periphery to the very center of modern scientific reasoning. The intellectual landscape of the early 20th century offered little fertile ground for the kind of reasoning Thomas Bayes had proposed. The statistical world was undergoing its own revolution, one led by titans like Ronald A. Bayesian, Jerzy Neyman, and Egon Pearson. Their frequentist framework provided powerful, objective-seeming tools, p-values, confidence intervals, hypothesis testing that were perfectly suited to the burgeoning fields of agricultural science, industrial quality control, and clinical trials. This paradigm defined probability as the long-run frequency of an event, a concept with immense practical utility. It sidestepped the thorny, philosophical issue of assigning probabilities to beliefs or hypotheses, a core element of the Bayesian approach. For a time, the elegant logic of updating belief lay dormant, a relic preserved within the advanced theory of probability, awaiting a new set of champions and a new class of problems that frequentist methods alone struggle to address. The revival began, as it so often does, at the frontiers of science, where existing tools proved inadequate. The Cambridge geophysicist Harold Jeffreys, grappling with inferring the structure of the Earth from sparse and noisy seismic data, found the frequentist prohibition on assigning probabilities to scientific theories deeply unsatisfying. His life's work was precisely that of weighing the evidence for competing hypotheses about the planet's core or the age of its crust. For Jeffreys, probability was the very language of scientific inference. His monumental 1939 work, Theory of Probability became the foundational text of the 20th century Bayesian movement. In it, he directly confronted the most persistent criticism of Bayes' theorem of the subjective nature of the prior probability. Jeffreys sought to create a system of objective Bayesianism, developing what are now called Jeffreys-Pryor's Pry distributions, designed to represent a state of minimal information. He built upon Laplace's earlier principle of indifference, aiming for a more rigorous formulation that would be invariant to parameterization, thereby providing a consistent, principled starting point for scientific inquiry. Jeffreys' work directly influenced a generation of scientists who felt a similar disconnect between the formalisms of frequentist statistics and the actual practice of scientific reasoning. This philosophical groundwork was powerfully complemented by the intensely practical work of figures like Irving John Good, a brilliant mathematician who worked alongside Alan Turing to crack the Enigma code at Bletchley Park during the Second World War. Good experienced the power of Bayesian updating in the most high-stakes environment imaginable. Every intercepted German message was a piece of new data, and the cryptanalysts constantly revised their beliefs about the Enigma machine's settings. This experience shaped Good's entire intellectual outlook. He developed the concept of the Bayes factor, a ratio that quantifies the evidence a piece of data provides for one hypothesis over another. This gave researchers a concrete, interpretable metric for model comparison, moving Bayesian analysis from a general philosophy to a specific quantitative procedure. Good's advocacy was relentless, and his ideas found a receptive audience among those, like himself, who saw statistics as a dynamic tool for learning and decision-making under profound uncertainty, a direct legacy of his formative years in military intelligence. The movement gained its full academic coherence through the efforts of Dennis Lindley. Initially trained in the frequentist tradition, Lindley underwent a profound intellectual conversion, becoming the most articulate and formidable advocate for the complete supremacy of the Bayesian viewpoint. He argued with mathematical rigor that any system of inference that deviates from the axioms of probability, as expressed through Bayes' theorem, is logically incoherent and can lead to demonstrably poor decisions. Lindley's work, particularly his 1972 book Bayesian Statistics, a review established the deep connections between Bayesian inference and decision theory, framing the entire enterprise as the sole rational approach to learning from data. He mentored a new generation of statisticians, creating a formal academic lineage that would carry the Bayesian paradigm into universities and research institutions worldwide, ensuring its intellectual survival and eventual flourishing. Yet, even with the philosophical foundations solidified by Jeffreys, the practical tools advanced by Good, and the axiomatic rigor provided by Lindley, a formidable barrier remained to computation. The mathematical heart of Bayes' theorem involves an integration step to calculate the evidence term in the denominator. For simple textbook problems, this interval is tractable. For the complex, high-dimensional models required by modern science models with hundreds or thousands of parameters, calculating this interval was analytically impossible and computationally prohibitive. The Bayesian promise of a complete posterior probability distribution remained, for most realistic applications, a theoretical ideal locked behind an impenetrable wall of mathematics. The key that unlocked this door came from a completely different field of statistical physics. In the 1950s, scientists at Los Alamos, including Nicholas Metropolis and his colleagues, were working on simulating the behavior of atomic systems. To do this, they developed a clever computational trick, a method for generating a sequence of random samples that, after an initial period, would be drawn from a desired probability distribution, even one that could only define up to a constant of proportionality. This was the birth of the Metropolis algorithm. Decades later, the statistician W.K. Hastings generalized this method in 1970, and the statistician brothers Stewart and Donald Gemin, in a landmark 1984 paper on digital image restoration, introduced a special case known as the Gibbs sampler. Together, these techniques formed the family of Markov chain Monte Carlo, or MCMC, methods, the insight was revolutionary. Instead of trying to solve the impossible integral to find the exact shape of the posterior distribution, MCMC allowed researchers to generate a large set of sample parameter values asterisk from asterisk the posterior distribution. By examining the properties of the sample, its mean, its variance, its quantiles, one could approximate the posterior distribution to any desired degree of accuracy. The intractable problem of integration was replaced by the far more manageable, albeit computationally intensive, problem of simulation. The advent of powerful, affordable digital computers turned this theoretical possibility into a practical reality. Suddenly, physicists could model complex particle interactions, geneticists could untangle a web of gene regulatory networks, and machine learning engineers could build sophisticated probabilistic models. For example, the Gemini brothers' application of the Gibbs sampler allowed them to take a noisy, corrupted digital image and, by treating the true pixel values as unknown parameters in a Bayesian model, reconstruct a clean, coherent image. This tangible success demonstrated the immense power of combining Bayesian modeling with MCMC computation, inspiring a torrent of applications across countless disciplines, and heralding the true dawn of the modern Bayesian age. The quiet Presbyterian minister from Tunbridge Wells would likely find the world his ideas now inhabit quite bewildering, a world saturated with data, where algorithms derived from his single posthumous essay guide the search for new medicines, pilot autonomous vehicles, and fell to the ceaseless torrent of digital communication. The journey from a handwritten manuscript, rescued from obscurity by Richard Price, to the computational part of 21st century science is a testament to the enduring power of a foundational concept. Bayes' ultimate contribution was a piece of intellectual machinery for reasoning through uncertainty, an engine for learning that would lie dormant for nearly 2 centuries, awaiting the fuel of computational power and the complex problems of the modern era to reveal its full potential. His legacy, therefore, manifests as a comprehensive framework for thought, a system of reasoning that extends far beyond a solitary theorem. The formula itself, expressing the probability of the hypothesis given the data, is elegant, yet its true significance lies in the philosophical orientation it codifies. It provides a formal language for the intuitive process of updating our beliefs in the light of new evidence. This simple, powerful idea recasts science itself. The scientific method becomes a specific, highly refined application of the Bayesian cycle. Formulate a hypothesis of prior belief, gather evidence, the data, and then update the plausibility of that hypothesis, the posterior belief. This posterior then becomes the prior for the next round of inquiry. It is a dynamic, iterative, and profoundly honest depiction of how knowledge is actually built, piece by piece, observation by observation. Pierre-Simon Laplace saw this potential, expanding the theorem into a grand theory of inference. Modern computation, through the brute force elegance of Markov chain Monte Carlo methods, finally provided the means to apply the theory to problems of staggering complexity, ones Laplace himself could only dream of solving. The impact of this computational flourishing has been twofold, creating parallel streams of influence that define the modern Bayesian landscape. One stream is intensely pragmatic, a toolkit of unparalleled utility. In this guise, Bayesian methods are the workhorses of applied statistics and machine learning. They power the A/B testing systems that optimize user experiences on websites, allowing companies to weigh evidence for competing designs. They underpin the diagnostic software that assists physicians in interpreting medical scans, calculating the probability of a condition given a set of symptoms and imaging results. The spam filter in your email client is a beautiful, everyday example of a naive-based classify at work, constantly updating its model of what constitutes an unwanted message based on the words you mark as spam. This practical legacy is one of demonstrable, quantifiable success, solving real-world problems with probabilistic sophistication. The other stream is deeply philosophical, offering a coherent epistemology for science and learning. Bayesian inference provides a natural framework for incorporating prior knowledge, a process that every working scientist performs implicitly. It formalizes the principle of Occam's razor through the Bayesian model comparison, where more complex models are penalized unless they provide a substantially better fit to the data. It offers a definition of probability as a degree of belief, a conception that allows one to speak meaningfully about the probability of a unique event, such as the truth of a specific scientific theory, a task that proves awkward for a frequentist interpretation based on long-run frequencies. This philosophical legacy provides a rich, unified language for discussing evidence, belief, and uncertainty, influencing fields from jurisprudence to the philosophy of science itself. Yet, the story of Bayesianism remains a living, evolving narrative with its own internal tensions and frontiers of exploration. The most persistent and intellectually fertile of these is the debate surrounding the choice of prior probabilities. The prior represents our state of knowledge before observing the data, and its selection can influence the final posterior conclusion. Critics have long pointed to the potential for subjectivity, arguing that different researchers with different priors could reach different conclusions from the same data. This challenge has spurred a vast and sophisticated body of research. The work of figures like Edwin T. Jaynes, who championed the principle of maximum entropy, represents a profound attempt to establish objective, information-based methods for selecting priors, turning the choice from a personal belief into a formal consequence of the available background information. This quest for uninformative or objective priors continues to drive theoretical statistics, seeking to build a version of Bayesian inference that is as impartial as possible. Simultaneously, the computational frontier continues to advance. While MCMC methods unlock the door to modern Bayesian analysis, the computational expense can be prohibitive for the truly massive datasets characteristic of big data. This has led to the development and popularization of alternative approximation techniques, such as variational inference, which trade some accuracy for significant gains in speed. The emergence of probabilistic programming languages, sophisticated software environments like Stan and PyMC, has further democratized Bayesian modeling. These tools abstract away much of the complex mathematics and algorithmic implementation, allowing domain experts in fields like biology, economics, and sociology to specify and fit complex Bayesian models with greater ease. The future of Bayesian practice lies in the synergy of these ever more powerful algorithms and increasingly accessible tools, pushing the boundaries of what can be modeled and understood. Reflecting on the entire arc of this history, from a quiet study in Tunbridge Wells to the global network of supercomputers running Bayesian algorithms, one is struck by the peculiar nature of intellectual inheritance. Thomas Bayes sought to address a specific problem of inverse probability, likely motivated by a desire to provide a rational foundation for belief in the face of Hume's skepticism. He was a careful, meticulous thinker who chose to withhold his most significant work from publication. He could never have envisioned that his name would become an adjective, a banner for a school of thought, or a verb describing a fundamental mode of data analysis. His legacy is an ultimate, and perhaps ironic, validation of his own theorem. A weak prior belief in the significance of his work has been updated by 2.5 centuries of evidence, culminating in a posterior belief of its monumental importance that approaches certainty. The quiet minister's private speculation became the public's engine of discovery, a powerful illustration that the true measure of an idea is its capacity to be adopted, adapted, and amplified by generations of minds to come.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.